Your garden hose pushes water at about 50 psi. A fire truck pump generates up to 250, enough to knock a grown adult off their feet while moving 1,500 gallons per minute. A bathtub filled every 5 seconds. But here's what most people miss. The onboard tank runs dry in under 3 minutes. So how does a fire truck keep pushing water across such enormous distances? It starts with a single spinning disc. A garden hose delivers water at around 50 psi. That's enough to rinse a driveway, but not even close to what's needed to battle a wall of flames. A fire truck's pump, by contrast, can generate pressures between 150 and 250 psi, 3 to 5 times higher. The difference isn't just in force, it's in volume. A typical garden hose might move 8 gallons per minute. The pump on a modern fire engine can push out anywhere from 500 to 1,500 gallons per minute. At full output, that's enough water to fill a standard bathtub every 5 seconds or drain a 1,000-gallon onboard tank in less than a minute, if running flat out. The scale is staggering. Firefighters routinely handle hoses that, at 250 psi, can knock a grown adult off balance. The water doesn't just trickle out. It explodes from the nozzle in a thick, heavy stream, capable of reaching the upper floors of a building or cutting through the heat of a fully involved structure fire. The pressure is powerful, but it's the sheer amount of water that makes the difference. Where a pressure washer boasts 3,000 psi, but moves only a few gallons per minute, a fire truck sacrifices extreme pressure for overwhelming volume. That's the secret to extinguishing a blaze. Not a needle-sharp jet, but a continuous flood. These numbers reveal the gulf between everyday plumbing and emergency response. The real story isn't the water stored in the tank. It's the relentless supply the pump can deliver, minute after minute, long after the tank itself is empty. The question is, how does a single machine produce that kind of force and flow? The answer lies in the engineering at the heart of every fire truck. Maya Alvarez stands at the pump panel, her gloved hand poised over the PTO switch. With a deliberate motion, she engages the clutch, and a deep mechanical thrum ripples through the truck. Under the hood, a Detroit diesel 8V92T engine rated at 540 brake horsepower and delivering 1,800 foot-pounds of torque roars to life. This is not just raw power for the wheels. Through a heavy-duty gear set known as the power takeoff, or PTO, a portion of that muscle is channeled directly into the pump system. The PTO's gear ratio, typically between 2:1 and 4:1, transforms the engine's rotational force, spinning the pump's impeller at a blazing 1,500 to 2,000 revolutions per minute. Think of the impeller as a turbine blade whirling inside a sealed housing. As it spins, it grabs water at the center and flings it outward, using centrifugal force to accelerate the fluid. The faster the impeller turns, the more energy it imparts. At full throttle, the pump acts like an amplifier, taking the steady rhythm of the diesel engine and boosting it into a torrent of hydraulic force. This is the core mechanism that bridges the gap between engine specs and the relentless stream at the nozzle. The analogy is simple. In a passenger car, 2,000 RPM means cruising at highway speed. In a fire truck, that same RPM is harnessed to move water, not wheels. The result is a continuous, high-volume flow, hundreds or even thousands of gallons per minute, delivered at pressures strong enough to reach the upper stories of a burning building. Every component, from the PTO clutch to the impeller's vanes, is engineered for sustained, high-stress operation. The entire system is designed to convert diesel horsepower into a controlled flood, ready to overwhelm fire with sheer volume. In this way, the fire truck's pump becomes more than a machine. It's the beating heart of every emergency response. A pressure washer blasts out 3,000 psi, enough to strip paint from concrete. But at just 2 to 4 gallons per minute, It would take nearly half an hour to fill a bathtub. In firefighting, that kind of pinpoint force is useless. What matters is sheer volume. A fire truck's pump might run at only 150 to 250 psi, but it moves hundreds of gallons every minute. At full throttle, a modern engine can deliver 1,500 gallons per minute, enough to fill a standard bathtub in 5 seconds flat. That's not a trickle, it's a flood. The numbers behind the truck's onboard tank tell a brutal truth. Even the largest municipal engines carry between 500 and 1,000 gallons. At a standard attack flow of 300 gallons per minute, a 1,000-gallon tank runs dry in just over 3 minutes. A smaller 500-gallon tank can be empty in less than 2. Push the pump to its maximum, say 1,200 gallons per minute, and the tank is gone in under 30 seconds. The tank, then, is just a launch pad. Sustained firefighting depends on a continuous supply, not a finite reservoir. This is the myth that needs breaking. High PSI does not equal firefighting power, and tank size is never the limiting factor. A garden hose, a pressure washer, even the biggest home water tank, none can match what a fire truck does every day. The engine's real weapon is relentless flow. Volume, not pressure, is what cools a burning structure and keeps the fire from roaring back. The pump's job is to turn every available gallon into an unbroken, overwhelming stream. When the tank empties, the clock is ticking. The crew must secure a new source or risk running dry, because in a real fire, every second and every gallon counts. Maya's eyes flick to the pressure gauge as she flips the primer switch. In firefighting, the first 30 seconds at the pump panel are unforgiving. If air remains trapped inside the pump housing, the impeller spins uselessly. No pressure, no flow, just the hollow roar of wasted horsepower. The difference between a primed pump and an AIR-locked one is not academic. A single pocket of air can slash discharge pressure by 30%, and a full airlock can drop output to less than 10% of what's needed. With a structure fire growing by the second, there's no time for error. The process is a practiced drill. Maya connects the supply hose, opens the intake, and engages the primer. For a vacuum primer, the Venturi draws air from the pump in 12 to 18 seconds. Positive displacement primers, like the rotary gear model on her engine, can clear the system in as little as 8 seconds. The pressure needle rises, slowly at first, then surging as water fills the void. Only when the last bubble escapes does the pump deliver its promised 150 to 250 psi. For Maya, every second counts. The National Fire Protection Association requires that 80% of rated flow be achieved within 30 seconds. Fail, and the fire wins precious ground. Suction lift adds another layer of risk. If the water source sits more than 8 feet below the pump, vacuum primers struggle, extending the purge time and threatening a total airlock. At high altitude, the thinner air further reduces suction power, stretching priming times to 40 seconds or more. In these moments, the pump operator's focus is absolute. Miss a step, and the stream at the nozzle falters, sometimes dropping by 20 psi or more, cutting reach by over 10 feet. The margin for error is razor thin. In the world of fire pumps, priming is not a formality. It's the difference between a lifeline and a silent, powerless machine. Long before diesel engines and PTO clutches, firefighting relied on raw muscle and patience. In the 17th century Amsterdam, crews gathered around hand lever pumps, wooden boxes fitted with pistons and iron handles. Each pull moved about 5 gallons, but it took a team of 4 to keep the water flowing, and the range rarely exceeded a few meters. These early machines were ingenious for their time, but they could never outpace a spreading fire. By the mid-1800s, steam power arrived. Now, a fire crew could summon real pressure, enough to shoot water up to the second floor. But steam engines came with their own limits. Before the first drop could be delivered, the boiler needed 15 to 20 minutes to reach operating temperature. In a city built of wood, those lost minutes often meant disaster. The breakthrough came with the centrifugal pump. Instead of pistons or steam, it used a spinning impeller to fling water outward, creating continuous flow at moderate pressure. This design, first refined in the late 19th century, became the backbone of modern fire apparatus. The same principle now powers everything from irrigation systems to city water mains. Centrifugal pumps are so widespread that, according to the Hydraulic Institute and the International Energy Agency, they account for nearly 10% of the world's total electricity use. From municipal water towers to oil refineries and skyscraper sprinklers, their reach extends far beyond the fireground. Johan van der Meer, a Dutch engineer, once described the centrifugal pump as a silent lifeline, hidden beneath every city. Today, that lifeline is everywhere, moving water, chemicals, even sewage, across continents and through the veins of modern civilization. What began as a wooden lever in a crowded square has grown into an invisible network, quietly shaping the safety and health of billions. Today, the centrifugal pump stands as the engineered backbone of firefighting, delivering thousands of gallons per minute over long distances, not by brute pressure, but by sheer volume and precision. As urban density grows and fire risks intensify, the science behind these pumps remains a frontline defense. Thanks for watching.